In the silent tension of the early Cold War, the world was divided not only by ideology, but by distance, time, and the limits of human perception. By the late 1950s, the United States faced a strategic vulnerability that could not be solved with diplomacy or firepower alone. It could not see clearly into hostile territory. Intelligence depended on reconnaissance aircraft that flew high but not fast, aircraft that relied on altitude as protection in an era when radar systems and surface-to-air missiles were advancing at an unforgiving pace. That illusion of safety collapsed decisively in 1960 when a U-2 spy plane was shot down over Soviet airspace. The message was unmistakable. The sky was no longer a sanctuary. Survival would now depend on speed, altitude, and engineering audacity beyond anything aviation had yet achieved. This moment exposed a fundamental problem of the modern world. Information had become the most valuable strategic asset on the planet, yet gathering it was growing more dangerous with each technological leap. Nations were expanding, missile silos were being built in remote regions, and military capabilities were evolving behind closed borders. Decision-makers needed timely, accurate intelligence, not days or weeks later, but now. Satellites were still in their infancy, limited in resolution and flexibility. What was required was a new kind of aircraft, one that could compress geography itself, cross continents in hours, and return with data that could reshape global strategy. Out of this necessity emerged a vision that bordered on the impossible. The requirement was deceptively simple: an airplane capable of sustained flight above Mach 3, at altitudes exceeding 80,000 feet, with enough range to span oceans and enough reliability to do it repeatedly. It had to operate in hostile environments where interception was not merely likely, but expected. This aircraft would not rely on stealth in the modern sense. Its survival would be based on a different principle entirely. If it was seen, it would already be gone. The responsibility for turning this vision into reality fell to Lockheed's Advanced Development Programs Division, better known as the Skunk Works, under the leadership of Clarence Kelly Johnson. Johnson was an engineer shaped by crisis and constraint. He believed that radical performance could only come from radical simplification, ruthless discipline, and a willingness to discard conventional thinking. To him, the problem was not how to improve existing aircraft, but how to redefine the physical limits of atmospheric flight. What his team was about to attempt was not an evolution. It was a rupture with everything that had come before. From the very beginning, the aircraft that would become the State Route 71 Blackbird was constrained not by imagination, but by physics. At speeds above Mach 3, air itself becomes an adversary. Friction heats the skin of the aircraft to temperatures that can exceed 900 degrees Fahrenheit. Traditional aluminum structures would soften, deform, and fail. Steel could withstand the heat, but its weight would make the aircraft incapable of reaching the required speeds and altitudes. The solution lay in titanium, a metal prized for its strength-to-weight ratio and thermal resilience, yet notoriously difficult to machine and form. Titanium introduced its own cascade of challenges. It reacted aggressively with oxygen and nitrogen at high temperatures, requiring entirely new manufacturing processes. Even more paradoxical was its supply. At the height of the Cold War, the largest sources of high-quality titanium were controlled by the Soviet Union. Through a web of shell companies and intermediaries, the United States quietly purchased tons of Soviet titanium to build an aircraft designed to spy on the Soviet Union. The Blackbird was, from its inception, a monument to the contradictions of geopolitics and global interdependence. The aircraft's shape was dictated entirely by aerodynamic necessity. Its long, needle-like fuselage reduced drag at supersonic speeds, while sharply swept delta wings provided stability and lift in the thin air of the stratosphere. Every curve, every angle, every seam was optimized for one purpose: sustained high-speed flight. Even the iconic black paint was functional, designed to radiate heat more effectively and reduce thermal stress during flight. This was an aircraft that leaked fuel on the ground because its tanks were designed to seal only when the structure expanded at operating temperature. It was not meant to be comfortable, efficient, or forgiving. It was meant to survive where nothing else could. Perhaps the most revolutionary aspect of the Blackbird was its propulsion system. The engines, designated Pratt and Whitney J58, were not conventional turbojets. At cruising speed, they functioned more like ramjets, with the majority of thrust generated not by the engine core, but by the controlled compression of incoming air. Specialized inlet cones adjusted automatically at supersonic speeds, slowing and shaping the airflow with shock waves that allowed the engines to operate efficiently at Mach numbers once thought unattainable for air-breathing propulsion. In effect, the State Route 71 was part airplane, part missile, and part spacecraft, operating at the edge of atmospheric flight. The risks were immense. Financially, the program consumed vast resources for an aircraft that would never be produced in large numbers. Politically, it represented a bold escalation in technological competition, one miscalculation away from international crisis. Operationally, every flight pushed the limits of materials science, aerodynamics, and human endurance. Yet the potential payoff was unparalleled. If successful, the Blackbird would give the United States a strategic advantage measured not in weapons, but in awareness. When the aircraft finally took to the skies, it did more than meet expectations. It shattered them. The State Route 71 could fly from New York to London in just over 3 hours. It could survey vast swaths of territory in a single mission, delivering intelligence that once required fleets of aircraft or weeks of analysis. It rewrote the rules of reconnaissance, rendering entire air defense systems strategically irrelevant. Missiles could be launched, interceptors scrambled, but none could catch it. The Blackbird did not evade threats. It outran them. Beyond its military role, the State Route 71 had a profound socioeconomic and psychological impact. It demonstrated that engineering excellence could overcome barriers of distance and time on a planetary scale. It accelerated the development of advanced materials, propulsion systems, and thermal management techniques that would later influence both military and civilian aerospace programs. It inspired generations of engineers, scientists, and designers to think beyond incremental improvement and embrace audacious goals. Culturally, the Blackbird became an icon of human ambition. Its sleek silhouette and unmatched performance symbolized the belief that no boundary was absolute. Though its missions were shrouded in secrecy, its reputation spread quietly through the aerospace community and into public consciousness. Even decades after its retirement, no operational aircraft has surpassed its speed or altitude. The State Route 71 remains a benchmark, not just of performance, but of intent. In the story of the Blackbird, the lesson is clear. Progress is not driven solely by necessity, nor by competition, but by the willingness to confront the impossible with discipline, creativity, and resolve. The State Route 71 did more than fly faster than any other airplane in history. It connected continents in hours, reshaped global intelligence, and proved that engineering, when pushed to its limits, can redefine the scale at which humanity operates. The history of aviation is written not only in wings and engines, but in the courage to challenge the boundaries of the possible. What followed the Blackbird's first successful demonstrations was not a period of comfort or confidence, but an escalation of complexity that pushed the program into uncharted territory. The State Route 71 was now proven possible, but possible did not mean mature, and it certainly did not mean safe. Every flight exposed new interactions between heat, speed, pressure, and human limits. At Mach 3, aviation no longer behaved like aviation. It became an exercise in controlled survival inside an environment that actively tried to destroy the machine operating within it. Thermal stress dominated every aspect of the aircraft's existence. As the Blackbird accelerated through the sound barrier and beyond, skin temperatures rose so dramatically that the airframe expanded several inches in length. This expansion was not an anomaly. It was an expected operating condition. Engineers had to abandon the traditional idea of rigid tolerances and instead design an aircraft that functioned like a living structure, growing and shrinking with temperature. Panels that appeared misaligned on the ground were perfectly aligned at cruise. Seals that leaked fuel during taxi became tight and secure at altitude. The State Route 71 was not broken on the runway. It was unfinished until it reached Mach 3. Fuel itself became part of the engineering solution. Conventional jet fuel would vaporize under the extreme temperatures generated by sustained supersonic flight. The Blackbird required a specialized fuel with a high flash point, chemically stable under heat, and capable of serving a secondary purpose as a heat sink. Before combustion, fuel was circulated through critical components to absorb thermal energy, cooling systems that would otherwise overheat. In effect, the aircraft used its own fuel to survive long enough to burn it. This integration of propulsion, cooling, and structural integrity was unprecedented in aviation. The engines, already revolutionary in concept, proved to be among the most challenging systems to master. The Pratt & Whitney J58 was neither a conventional turbojet nor a pure ramjet. At takeoff and low speeds, it behaved like a traditional jet engine, inefficient but controllable. As speed increased, the engine transitioned into a hybrid mode where the majority of thrust was generated not by the turbine, but by the inlet system and exhaust geometry. At cruise, more than half of the thrust came from the inlet itself, transforming the entire front of the aircraft into a propulsion system. This delicate balance depended on precise control of shock waves inside the engine inlet. A slight miscalculation could cause an unstart, a violent disruption of airflow that resulted in sudden loss of thrust and extreme yaw forces. An engine unstart at Mach 3 was not merely uncomfortable. It was dangerous. The asymmetric thrust could throw the aircraft off course with brutal force, testing both the airframe and the pilot. Crews trained relentlessly to recognize and manage these events, but the margin for error was slim. Automation assisted, but ultimate responsibility rested with human judgment operating at the edge of reaction time. Flying the Blackbird was not about aggressive maneuvering. It was about restraint, anticipation, and trust in systems that had no historical precedent. Navigation posed another existential challenge. At speeds exceeding 2,000 miles per hour, even minor navigational errors compounded rapidly. Traditional inertial navigation systems drifted over time, and celestial fixes used in earlier aviation were impractical at such velocities. The solution was an advanced hybrid system that combined inertial navigation with stellar observation. Sensors tracked the position of stars even in daylight, continuously correcting the aircraft's position. This was not simply a technological novelty. It was a necessity. Without it, the Blackbird could not reliably reach its targets or return home. Human endurance became a critical limiting factor. The State Route 71 routinely operated at altitudes where atmospheric pressure was insufficient to sustain life. A loss of cabin pressure would render a pilot unconscious in seconds. To mitigate this risk, crews wore full-pressure suits similar to those used by astronauts. These suits were bulky, restrictive, and unforgiving, yet essential. Every mission required hours of preparation, including pre-breathing pure oxygen to purge nitrogen from the bloodstream and prevent decompression sickness. The pilots were not just flying an aircraft. They were managing their own survival systems while executing missions of strategic importance. The political stakes surrounding each flight were equally severe. Every mission penetrated regions of intense geopolitical sensitivity. Although the Blackbird often remained outside sovereign airspace, its presence was unmistakable. Radar systems detected it. Interceptors were launched. Missiles were fired. None succeeded. The aircraft's speed rendered reaction futile, but the attempt itself carried risk. A mechanical failure at altitude over hostile territory would leave no margin for rescue. The loss of State Route 71 would not only be a technological setback, it would be a political shockwave. Despite these risks, operational demand for the Blackbird increased. Its performance fundamentally altered intelligence planning. Instead of relying on static observation platforms or slow reconnaissance flights, analysts could now request targeted missions with rapid turnaround. The aircraft's ability to collect high-resolution imagery across vast distances in a single sortie compressed intelligence cycles dramatically. Decisions that once depended on outdated or incomplete data could now be informed by near real-time observation. This compression of time had profound strategic consequences. Faster intelligence reduced uncertainty, and reduced uncertainty lowered the risk of catastrophic miscalculation. In an era defined by nuclear brinkmanship, this mattered. The State Route 71 did not carry weapons, but it influenced the deployment of weapons worldwide. Missile sites could be monitored, troop movements observed, infrastructure assessed. In doing so, the Blackbird became a stabilizing force, quietly shaping policy without firing a shot. The economic cost of maintaining such capability was enormous. Each flight hour consumed vast quantities of fuel and required intensive maintenance. Specialized crews inspected the aircraft after every mission, examining panels, seals, and engines stressed to their limits. Parts were replaced not because they had failed, but because failure was unacceptable. This philosophy of preventative perfection drove costs higher, but ensured an unmatched safety record. Remarkably, no State Route 71 was ever lost to enemy action, and none were lost due to structural failure at speed. As experience accumulated, the Blackbird evolved. Incremental refinements improved reliability, sensor capability, and mission flexibility. Cameras became more advanced. Electronic intelligence systems grew more sophisticated. Data processing improved, allowing information to be delivered faster and with greater clarity. Yet the core architecture remained unchanged. The fundamental design was already operating so close to physical limits that radical modification was neither feasible nor necessary. Within the aerospace community, the State Route 71 became a reference point. Engineers spoke of it not as a machine, but as a benchmark. Problems that seemed insurmountable in other programs were reframed with a simple question. If this can survive Mach 3, why can't we solve this? Its influence extended into spacecraft design, high-speed aerodynamics research, and materials science. Lessons learned from managing thermal expansion, airflow control, and integrated systems informed projects far removed from reconnaissance aviation. Over time, external factors began to shift. Satellites improved, offering persistent coverage without risking pilots or airframes. Advances in digital imaging and orbital mechanics reduced the unique advantages of manned high-speed reconnaissance. Budgets tightened. Strategic priorities changed. The Blackbird, extraordinary as it was, became increasingly difficult to justify in purely economic terms. Yet this transition did not diminish its achievement. The State Route 71 had fulfilled its purpose not only operationally, but intellectually. It proved that speed could be a form of defense. It demonstrated that engineering solutions could overcome problems once considered absolute barriers. It showed that with enough discipline, innovation, and acceptance of risk, the atmosphere itself could be reshaped into a domain of strategic control. The second chapter of the Blackbird story is therefore not about triumph alone, but about endurance. Endurance of materials under heat, of systems under stress, of humans under pressure, and of political will under uncertainty. It is the story of an aircraft that survived not because it was invulnerable, but because it was designed with an uncompromising understanding of reality. In pushing so far beyond the known boundaries of flight, the State Route 71 forced the world to reconsider where those boundaries truly lay. The moment the Blackbird transitioned from a classified engineering gamble into an operational reality marked a turning point not just for the program, but for aviation as a whole. When the State Route 71 entered active service, it did so quietly, without public fanfare or ceremonial rollout. There were no crowds, no grand declarations. Its arrival was defined instead by results. From its earliest missions, the aircraft demonstrated capabilities so far beyond existing platforms that entire assumptions about reconnaissance, response time, and global reach had to be rewritten. The first operational flights revealed an aircraft that did not merely fly fast, but redefined what speed meant in a strategic context. The State Route 71 could launch from the continental United States, accelerate to cruising speed in the stratosphere, cross oceans, survey targets thousands of miles away, and return home within a single duty cycle. Missions that once required forward bases, diplomatic clearances, and vulnerable refueling chains were now executed with unprecedented autonomy. Geography, which had always imposed limits on military planning and political response, suddenly mattered far less. The numbers alone conveyed the scale of the paradigm shift. Cruising above Mach 3, the Blackbird covered more than 2,000 miles per hour. It routinely operated above 80,000 feet, well beyond the effective reach of contemporary interceptors. Its operational ceiling placed it closer to low Earth orbit than to commercial air traffic. In practical terms, this meant that air defense systems designed around altitude or speed alone were rendered obsolete. Even when detected, response windows were measured in seconds, not minutes. By the time defensive systems reacted, The aircraft had already passed beyond engagement range. This performance translated directly into strategic leverage. Intelligence was no longer constrained by slow collection cycles or high attrition risk. The State Route 71 could be tasked dynamically, responding to emerging crises rather than static intelligence requirements. Missile tests could be observed shortly after launch. Infrastructure developments could be confirmed within hours. Troop movements could be assessed before they reached critical mass. This immediacy reshaped how policymakers thought about escalation, deterrence, and verification. The aircraft sensor suite played a central role in this transformation. High-resolution optical cameras, side-looking radar, and electronic intelligence systems allowed the Blackbird to collect data across vast swaths of territory in a single pass. Unlike satellites, which followed predictable orbits, the State Route 71 could be routed flexibly, focusing on areas of immediate concern. This adaptability made it uniquely valuable during periods of heightened tension, when uncertainty carried enormous risk. The psychological impact of this capability extended far beyond the intelligence community. For adversaries, the knowledge that an aircraft could appear without warning, observe critical assets, and depart before interception was possible created a persistent sense of exposure. Defensive doctrines built around denial and concealment were undermined by sheer speed. Even when airspace was not technically violated, the presence of the Blackbird just beyond borders influenced behavior. Infrastructure was hardened. Movements were disguised. Resources were diverted toward countermeasures that rarely proved effective. For allies, the State Route 71 became a symbol of technological reassurance. Its ability to provide accurate, timely intelligence reduced reliance on speculation and worst-case assumptions. Shared data strengthened alliances and improved coordination. In an era where misinterpretation could lead to irreversible decisions, this clarity mattered profoundly. The Blackbird did not prevent conflict by force, but by reducing ignorance, and in doing so, it quietly contributed to global stability. Operationally, the aircraft demanded a level of precision that matched its performance. Every mission was meticulously planned, accounting for atmospheric conditions, fuel consumption, sensor timing, and geopolitical sensitivities. Crews operated within narrow margins, where deviations of seconds or degrees could affect mission outcomes. Yet despite this complexity, the State Route 71 achieved a remarkable operational record. It flew thousands of sorties without a single loss to hostile action. This was not a product of luck, but of design philosophy. The aircraft did not rely on evasion or countermeasures. It relied on physics. As the Blackbird's reputation grew, so did its influence on aerospace thinking. Engineers and strategists alike began to reassess long-held assumptions about survivability. The State Route 71 demonstrated that speed could be a defensive strategy in itself. Rather than attempting to hide from threats, the aircraft simply rendered them irrelevant by operating outside their engagement envelope. This concept would echo decades later in the design of hypersonic systems and advanced spaceplanes, many of which trace their intellectual lineage back to the Blackbird. Economically, the program represented a complex trade-off. The State Route 71 was expensive to build, operate, and maintain. Each flight consumed resources disproportionate to conventional aircraft. Yet when measured against the strategic value of the intelligence it provided, its cost became more defensible. Prevented miscalculations, avoided escalations, and informed policy decisions carried value that could not be easily quantified. In this sense, the Blackbird functioned as an insurance policy against uncertainty, one whose dividends were paid in restraint rather than conquest. Culturally, the aircraft began to escape the confines of classification, at least in reputation. Though details of its missions remained secret, its existence became known, and with it, a sense of awe. Pilots from other platforms measured their careers against it. Engineers spoke of it in reverent terms. Within the aviation world, the State Route 71 was no longer just an aircraft. It was a statement, a declaration that the limits of flight were not fixed, but negotiated through ingenuity and risk. The Blackbird also altered the relationship between human and machine. At such extreme speeds and altitudes, pilots were no longer directly flying in the traditional sense. They were managing systems, interpreting data, and making strategic decisions while the aircraft maintained its own delicate balance. This shift foreshadowed later developments in automation, fly-by-wire systems, and eventually unmanned platforms. The State Route 71 was not unmanned, but it pointed toward a future where human cognition, rather than physical control, would become the pilot's primary role. As the years passed, the State Route 71 continued to adapt within the constraints of its original design. Sensor upgrades improved resolution and expanded intelligence capabilities. Communications systems evolved, allowing faster dissemination of data. Integration with broader intelligence networks enhanced its value as part of a system rather than a standalone platform. Yet even as it evolved, its core achievement remained unchanged. No other operational aircraft could match its combination of speed, altitude, and range. The broader paradigm shift introduced by the Blackbird extended beyond reconnaissance. It influenced how nations thought about global reach, response time, and the strategic use of technology. It demonstrated that engineering breakthroughs could alter geopolitical realities without altering borders. It showed that dominance did not always require presence, and that observation, when executed with precision and speed, could be as powerful as force. By the height of its operational life, the State Route 71 had become both indispensable and irreplaceable. No alternative platform offered the same combination of survivability and flexibility. Yet this uniqueness also carried the seeds of its eventual obsolescence. As technology advanced, particularly in space-based surveillance, the balance between risk, cost, and capability began to shift. The Blackbird remained unmatched, but it was no longer alone in its mission. Still, during its prime, the State Route 71 represented a moment when engineering ambition aligned perfectly with strategic necessity. It did not merely collect intelligence. It reshaped how intelligence was valued, delivered, and acted upon. It compressed the world, shortened decision loops, and reduced the fog that so often precedes disaster. In doing so, it marked a profound change in the relationship between technology and global power, a change measured not in explosions or victories, but in the quiet prevention of the unthinkable. Before the State Route 71 Blackbird made its unprecedented mark on aviation, the world was bound by a set of limitations that seemed insurmountable. Commercial aviation had made substantial strides in the post-World War II era, but the need for faster, more efficient aircraft was becoming more urgent as the geopolitical climate of the Cold War escalated. By the 1960s, the United States military had a clear need for a reconnaissance aircraft capable of flying at extraordinary speeds and altitudes to gather intelligence over enemy territory without putting pilots at significant risk. This was a time when aircraft design was constrained by the physics of propulsion and materials, where the boundaries of speed and altitude were confined by the limits of technology. The world needed an aircraft that could break those barriers. What was required was a machine that could push the limits of flight itself, reaching speeds that were previously thought unattainable for an operational aircraft. At the heart of this mission was a group of visionary engineers and designers working under a veil of secrecy that would lead them to the creation of the State Route 71 Blackbird, an aircraft that would redefine what was possible in aviation. The challenge was monumental. It wasn't simply about creating a faster plane. It was about overcoming obstacles that had never been tackled before in the history of aviation. The SR-71 was conceived during an era where aviation technology was in a race against time. With the Soviet Union gaining ground in the development of missile and reconnaissance technologies, the U.S. Air Force knew it needed an aircraft that could stay ahead of emerging threats. It required a plane that could fly faster than a missile could intercept and higher than any aircraft could reach. That's where the SR-71 came in, developed by Lockheed's renowned Skunk Works division. It was the result of over a decade of intense, almost feverish innovation. The key engineers behind this groundbreaking aircraft included Clarence Kelly Johnson, the head of Skunk Works, who had already made his name with earlier aircraft such as the P-38 Lightning and the U-2 spy plane. Johnson and his team of designers, along with military personnel who understood the operational requirements, faced the daunting task of creating a jet that could achieve Mach 3 speeds, 3 times the speed of sound, at altitudes that reached up to 85,000 feet. At that height, the air is thin, and the heat from traveling at such high speeds would be enough to melt most materials. The State Route 71 needed to be designed with materials that could withstand this extreme environment without sacrificing the speed or agility necessary for a successful reconnaissance mission. In addition to these technical challenges, the SR-71's designers faced a political and financial risk. The costs associated with the SR-71 program were astronomical, with each aircraft costing over $33 million in 1960s dollars, equivalent to nearly $250 million today when adjusted for inflation. For a project of this magnitude, it was not just a matter of designing the aircraft, but of convincing decision-makers that the aircraft was a necessary investment, even when conventional wisdom said it was impossible. Yet the sheer ambition of the project captivated everyone involved. This wasn't just another plane. It was a statement that human ingenuity, combined with cutting-edge technology, could overcome any challenge. The design of the SR-71 was unique in its form and function. The plane had a sleek, angular shape. Unlike any other aircraft before it, it was designed to be as fast and efficient as possible, with minimal drag. The aircraft's surface was crafted from titanium, a material that could withstand the extreme temperatures generated by air friction at Mach 3, while also being lightweight enough to not sacrifice speed. This was a departure from the materials typically used in aviation, where aluminum had been the standard for decades. The decision to use titanium was one of the many innovations that set the SR-71 apart from anything that had come before it. However, titanium presented a new set of challenges. It was difficult to work with, and at the time, it was not widely available. But Lockheed's engineers and technicians, working under Johnson's leadership, were able to forge new techniques for working with this challenging material. Titanium would become the cornerstone of the SR-71's construction, providing the strength necessary to withstand the extreme conditions of high-speed flight. Even the engines, the heart of any aircraft, had to be completely reimagined for the SR-71. The plane used turbojet engines equipped with afterburners that allowed it to reach incredible speeds. These engines were designed to burn fuel at a rate that could have drained the fuel tanks in a matter of minutes, but they were necessary to achieve the speeds and altitudes required. To ensure that the SR-71 could maintain these high speeds, the engines were designed to be operated at maximum capacity, essentially running on the edge of their limits. From the outset, the SR-71 program was not only a race against time, but also a battle against skepticism. Many questioned whether the technology even existed to build such an aircraft. How could a plane fly so fast and high while still gathering valuable intelligence? The SR-71's design was so far ahead of its time that, for many, it seemed impossible. Yet the engineers at Skunk Works were determined to prove that it could be done. But the SR-71 was not just a technological marvel. It was a symbol of the era, a symbol of the race for dominance in the Cold War, a time when the world seemed to teeter on the edge of technological and political conflict. The plane's design was a product of the intense desire to achieve something that no one thought was possible. It represented the pinnacle of human ambition, a machine that would not only carry out its intended purpose, but would leave an indelible mark on the history of aviation. Despite all the challenges, the Blackbird would emerge as the fastest aircraft ever built. In doing so, it would forever change the world of aviation, pushing the boundaries of what was possible and establishing the SR-71 Blackbird as a living legend in the skies. This was just the beginning. The story of the SR-71's creation was a testament to human perseverance and ingenuity, a legacy that continues to inspire aviation engineers and dreamers to this day. The story of the SR-71 Blackbird does not end with its final flight, nor with its retirement to museums and hangars. Its true conclusion exists in the enduring shift it forced upon aviation, engineering, and the way humanity understands the relationship between ambition and limitation. The Blackbird was never just an airplane. It was an argument made of titanium, heat, and velocity. An argument that said the boundaries of the possible are not fixed, but negotiated by those willing to confront them with discipline and imagination. When the SR-71 was finally withdrawn from service, it left behind a paradox. It had never been replaced. Decades later, no operational aircraft has surpassed its speed or altitude. In a world defined by rapid technological turnover, this fact is extraordinary. The Blackbird did not become obsolete because it was surpassed. It became unnecessary because the world around it changed. Satellites matured, digital sensors improved, and intelligence gathering shifted toward persistent, unmanned systems. Yet even in this new paradigm, the principles proven by the SR-71 continue to shape design philosophy. Speed as survivability, integration over brute force, systems engineered not for comfort, but for purpose. The aircraft's legacy is inseparable from the mindset that created it. The engineers of the Skunk Works operated under constraints that would seem unacceptable today. Minimal bureaucracy, absolute accountability, radical trust in small teams. Problems were solved not through endless iteration, but through decisive choices grounded in physics and experience. This culture of engineering excellence has become as influential as the aircraft itself. Programs across aerospace, defense, and even commercial technology trace their intellectual heritage to the methods refined during the Blackbird's development. Beyond engineering, the SR-71 reshaped how nations perceived distance and time. It demonstrated that the planet could be traversed in hours at the edge of space, collapsing the psychological gap between continents. This compression of distance foreshadowed the interconnected world that would later emerge through digital communication and global logistics. In its own way, the Blackbird was an early symbol of globalization, not through trade or culture, but through information. It made the world smaller by making observation faster. The socio-economic impact of this capability is subtle but profound. By reducing uncertainty, the SR-71 influenced decision-making at the highest levels. Crises informed by accurate intelligence are less likely to spiral into catastrophe. Misinterpretation thrives in ignorance. And the Blackbird was a tool designed to eliminate ignorance at unprecedented speed. Its value was not measured in victories, but in disasters avoided. This is a legacy that does not appear in headlines. Yet, it is among the most consequential contributions any aircraft has ever made. Culturally, the Blackbird occupies a unique place. It is admired not because it was armed, but because it was elegant in its purpose. Its beauty lies in function, in the ruthless optimization of form to mission. The aircraft inspires awe precisely because it represents restraint as much as power. It did not dominate the skies by force, but by existing beyond reach. In an age where technological prowess is often equated with visibility, the SR-71 reminds us that some of the most powerful tools operate quietly, almost invisibly, shaping outcomes without spectacle. The human dimension of the Blackbird's legacy is equally enduring. The pilots who flew it operated closer to space than to conventional flight, managing machines that offered no forgiveness for error. Their discipline, professionalism, and trust in engineering exemplified a partnership between human judgment and technological precision. As aviation moves increasingly toward automation and unmanned systems, this relationship remains central. The SR-71 showed that even at extreme performance, human cognition, decision-making, and responsibility remain indispensable. From a design perspective, the Blackbird stands as a warning and an inspiration. It warns that operating at the edge of physics demands sacrifice, cost, and relentless maintenance. There are no shortcuts at Mach 3, but it also inspires by proving that such extremes are achievable when objectives are clear and compromises are understood. Modern hypersonic research, advanced propulsion systems, and spaceplane concepts all echo questions first answered by the SR-71. How do materials behave under sustained heat? How do systems transition seamlessly across regimes? How does speed redefine survivability? Even its imperfections contribute to its legend. The fuel leaks, the demanding maintenance, the narrow operating margins were not flaws to be eliminated, but trade-offs accepted. The Blackbird teaches that perfection in engineering does not mean eliminating compromise, but choosing the right compromises in service of a higher goal. This lesson resonates far beyond aviation, into any field where innovation challenges established limits. Today, as the SR-71 rests behind ropes and glass, it continues to command attention. Visitors stand beneath its dark silhouette, often surprised by its size, its slenderness, its almost organic form. What they are witnessing is not just an artifact of the Cold War, but a physical manifestation of human ambition at its most disciplined. The Blackbird does not tell a story of reckless experimentation. It tells a story of calculated audacity, of pushing forward with eyes open to risk and consequence. In the broader narrative of aviation history, the SR-71 occupies a singular chapter. It represents a moment when necessity, technology, and vision aligned perfectly. It bridges the era between atmospheric flight and space exploration, between analog systems and digital integration. It is both a culmination of traditional aeronautical engineering and a precursor to futures still being explored. The enduring lesson of the Blackbird is not that faster is always better, but that clarity of purpose unlocks extraordinary potential. The SR-71 was designed to do one thing better than anything before or since, and every decision flowed from that focus. In an age often defined by multi-purpose platforms and compromise-driven design, this clarity stands as a powerful reminder of what can be achieved when ambition is paired with discipline. Ultimately, the SR-71 Blackbird reminds us that the history of aviation is not merely a progression of machines, but a record of human will. Each leap forward is written in steel, heat, and ingenuity, shaped by those willing to challenge accepted limits. The Blackbird did not simply fly faster than the world. It changed how the world could be understood, and in that achievement, its legacy endures. The history of aviation is written with steel, ingenuity, and the will to defy limits. The story of the SR-71 Blackbird does not end with its final flight, nor with its retirement to museums and hangars. Its true conclusion exists in the enduring shift it forced upon aviation, engineering, and the way humanity understands the relationship between ambition and limitation. The Blackbird was never just an airplane. It was an argument made of titanium, heat, and velocity, an argument that said the boundaries of the possible are not fixed, but negotiated by those willing to confront them with discipline and imagination. When the SR-71 was finally withdrawn from service, it left behind a paradox. It had never been replaced. Decades later, no operational aircraft has surpassed its speed or altitude. In a world defined by rapid technological turnover, this fact is extraordinary. The Blackbird did not become obsolete because it was surpassed. It became unnecessary because the world around it changed. Satellites matured, digital sensors improved, and intelligence gathering shifted toward persistent, unmanned systems. Yet even in this new paradigm, the principles proven by the SR-71 continue to shape design philosophy. Speed as survivability, integration over brute force, systems engineered not for comfort, but for purpose. The aircraft's legacy is inseparable from the mindset that created it. The engineers of the Skunk Works operated under constraints that would seem unacceptable today. Minimal bureaucracy, absolute accountability, radical trust in small teams. Problems were solved not through endless iteration, but through decisive choices grounded in physics and experience. This culture of engineering excellence has become as influential as the aircraft itself. Programs across aerospace, defense, and even commercial technology trace their intellectual heritage to the methods refined during the Blackbird's development. Beyond engineering, the SR-71 reshaped how nations perceived distance and time. It demonstrated that the planet could be traversed in hours at the edge of space, collapsing the psychological gap between continents. This compression of distance foreshadowed the interconnected world that would later emerge through digital communication and global logistics. In its own way, the Blackbird was an early symbol of globalization, not through trade or culture, but through information. It made the world smaller by making observation faster. The socio-economic impact of this capability is subtle but profound. By reducing uncertainty, the SR-71 influenced decision-making at the highest levels. Crises informed by accurate intelligence are less likely to spiral into catastrophe. Misinterpretation thrives in ignorance. And the Blackbird was a tool designed to eliminate ignorance at unprecedented speed. Its value was not measured in victories, but in disasters avoided. This is a legacy that does not appear in headlines. Yet, it is among the most consequential contributions any aircraft has ever made. Culturally, the Blackbird occupies a unique place. It is admired not because it was armed, but because it was elegant in its purpose. Its beauty lies in function, in the ruthless optimization of form to mission. The aircraft inspires awe precisely because it represents restraint as much as power. It did not dominate the skies by force, but by existing beyond reach. In an age where technological prowess is often equated with visibility, the SR-71 reminds us that some of the most powerful tools operate quietly, almost invisibly, shaping outcomes without spectacle. The human dimension of the Blackbird's legacy is equally enduring. The pilots who flew it operated closer to space than to conventional flight, managing machines that offered no forgiveness for error. Their discipline, professionalism, and trust in engineering exemplified a partnership between human judgment and technological precision. As aviation moves increasingly toward automation and unmanned systems, this relationship remains central. The SR-71 showed that even at extreme performance, human cognition, decision-making, and responsibility remain indispensable. From a design perspective, the Blackbird stands as a warning and an inspiration. It warns that operating at the edge of physics demands sacrifice, cost, and relentless maintenance. There are no shortcuts at Mach 3. But it also inspires by proving that such extremes are achievable when objectives are clear and compromises are understood. Modern hypersonic research, advanced propulsion systems, and spaceplane concepts all echo questions first answered by the SR-71. How do materials behave under sustained heat? How do systems transition seamlessly across regimes? How does speed redefine survivability? Even its imperfections contribute to its legend. The fuel leaks, the demanding maintenance, the narrow operating margins were not flaws to be eliminated, but trade-offs accepted. The Blackbird teaches that perfection in engineering does not mean eliminating compromise, but choosing the right compromises in service of a higher goal. This lesson resonates far beyond aviation, into any field where innovation challenges established limits. Today, as the SR-71 rests behind ropes and glass, it continues to command attention. Visitors stand beneath its dark silhouette, often surprised by its size, its slenderness, its almost organic form. What they are witnessing is not just an artifact of the Cold War, but a physical manifestation of human ambition at its most disciplined. The Blackbird does not tell a story of reckless experimentation. It tells a story of calculated audacity, of pushing forward with eyes open to risk and consequence. In the broader narrative of aviation history, the SR-71 occupies a singular chapter. It represents a moment when necessity, technology, and vision aligned perfectly. It bridges the era between atmospheric flight and space exploration, between analog systems and digital integration. It is both a culmination of traditional aeronautical engineering and a precursor to futures still being explored. The enduring lesson of the Blackbird is not that faster is always better, But that clarity of purpose unlocks extraordinary potential. The SR-71 was designed to do one thing better than anything before or since, and every decision flowed from that focus. In an age often defined by multi-purpose platforms and compromise-driven design, this clarity stands as a powerful reminder of what can be achieved when ambition is paired with discipline. Ultimately, the SR-71 Blackbird reminds us that the history of aviation is not merely a progression of machines, but a record of human will. Each leap forward is written in steel, heat, and ingenuity, shaped by those willing to challenge accepted limits. The Blackbird did not simply fly faster than the world. It changed how the world could be understood. And in that achievement, its legacy endures. The history of aviation is written with steel, ingenuity, and the will to defy limits.